It's just an LC.
Yes.
Don't have a case.
With quantity with price, not what food, not what Professor.
I'm Avik Dutt,
Get the answers.
and welcome to the FLoQuET lab. We started building the FLoQuET lab about 2 years ago, and our work focuses on photonics and quantum systems. Photonics is the modern science of light, in that we try to understand how to control, manipulate, and process light in a way that we want to use it for communications, computing, and sensing. And why do we want to do this? Because light is an extremely low loss and ultra high speed carrier of information, which makes it useful for building both practical technologies and for studying fundamental science. Our lab has a mix of graduate and undergraduate students and postdocs, each of them with a different and independent focus. Working collectively and collaboratively across a wide range of fields spanning engineering, applied physics, theoretical physics, and material science enables us to push the boundaries across many subdomains within photonics and quantum engineering, which I find really exciting. The story of the lab starts in my hometown, Kolkata, India. I was always a curious child, and along with the encouragement of family and teachers around, it drew me to science. I loved asking questions about things near and far away, and often designing some experiments to find answers. I remember once asking my mother if the stars in the night sky were within the Earth's atmosphere or outside. Another example that comes to mind, turmeric, which we use a lot in our food, turns red when mixed with soap. It was perhaps the first example of a litmus-like test way before chemistry class. My family members weren't huge fans of the incessant questions or sometimes crazy experiments, but beyond a point they realized that letting me be curious was perhaps worth the risk. Fast forward a few years, and I found myself pursuing a major in electronics engineering and a minor in physics at IIT Kharagpur. I really liked how engineering mixed theoretical focuses such as pure science and mathematics with practical applications and emphasized building and creating tangible things. When I was getting my degree, professors around encouraged me to look into a field gaining traction such as photonics, and it was really at the crossroads of some beautiful physics and calculus mixed with engineering applications which really interested me.
Hi, my name is Dhruv Srinivasan, and I'm an undergraduate physics and mechanical engineering student at the University of Maryland and a researcher with the FLoQuET group. Signals are all around us, from a simple Google search to scanning our world hundreds of kilometers above the ocean floor. Signals are at the heart of many of our technological innovations. This means that signals limit the growth of our technological innovations, namely through the rate at which we can produce signals, the energy efficiency of producing these signals, and the quality of these signals. This is where photonics comes in. Through generating, modulating, and measuring light, we're able to sense, communicate, and compute in better ways. Light can travel for incredibly long distances without losing energy. Contrast this to electricity, where energy can be lost very quickly based off of how long an electrical signal travels. This manifests as heat, and it's the reason why companies like Microsoft put data centers in the ocean to mitigate the effects of thermal loss as our signal goes through a wire. dB per kilometer is a measure of how much energy a signal loses for each kilometer a signal travels. Light loses only on average 0.3 dB per kilometer, while electrical signals on average lose almost 100 dB per kilometer, making light a much more energy efficient carrier of information. light is very easy to manipulate, making it a fruitful application for many different technologies. We can adjust the amplitude, frequency, and phase of light using modulators, and this allows us to imprint information onto light. When we adjust the frequency of light, we can represent audio. That's how AM and FM radio works. It's what allows you to listen to music on the go in your car, despite being very far from a radio station. Alternatively, we can change the amplitude of our signal to represent bits, where one amplitude represents 0 and another represents 1. We can then increase the frequency of this to send information very, very quickly. It's what allows you to play video games with your friend that's from across the world, FaceTime them, text them, or stream a 4K video. And finally, we can also adjust the phase of our signal, how much our signal shifts left and right over time. This allows us to create devices such as frequency combs, which allows us to measure our universe much, much faster than traditional electrical signals, in addition to enabling all sorts of exciting applications, such as LiDAR, which can later perhaps power autonomous vehicles.
That's what drew me to photonics, the mix of theoretical physics and practical applications. I think I realized I want to pursue a career in photonics around the end of my 3rd year. It was a field that had something I was good at reasonably, and a field where professors were willing to provide me with ample opportunities. In India, it is quite common to do an undergraduate thesis when we are pursuing an honors degree, and I did that in capillary optical fibers. The next steps to rigorously learn the field in depth was to do a PhD, and Cornell's nanophotonics group, led by Professor Michael Lipson, really intrigued me, and I started pursuing a PhD there. It was a big jump going from India to Cornell in the United States, where how people talked with each other and interacted was different. There were cultural differences, and just the way science was done. At Cornell, my research focused on practical applications of photonics, specifically nanophotonics, which deals with downscaling the sizes of devices below the width of a human hair. Specifically, we explored how nanophotonics could be used to create special states of light called squeezed light, and all of this allows us to create devices such as quantum computers and sensors. My PhD advisor, Michael Lipson, taught me to think about the big picture with my research in terms of not just how we were doing things, but why we were doing it. This inspired me to think about how to use ring resonators to make a difference. Rings are a building block for a plethora of photonic devices and systems, and hence they are very powerful.
Hi, I'm Sashank. I'm a 3rd year PhD student at the University of Maryland, and this is where ring resonators come in. Ring resonators allow us to modify light in many ways, and this ability to modify light allows for enhanced reading and decoding of signals. As a result, they have applications in computing, simulation, decoding signals, and communication, and even in the more exotic applications like generating quantum states of light. This allows us to do a lot of specialized tasks, but then it begs the question of what are ring resonators? So ring resonators are devices that deflect light in a circular path. A portion of the light that is coming in through a waveguide couples in through a coupler and goes in a circular path and comes back to the same point, and it either constructively or destructively interferes at this part of the ring resonator. Constructive or destructive interference occurs when you have two waves that are traveling either in phase, where it leads to the signals adding up, or when they're out of phase, and therefore they go to 0. So this constructive and destructive interference is what allows us to filter out a narrow set of frequencies and is quite useful in applications where you require only a narrow set of frequencies, like in communications. Now, these ring resonators can be used for multiple wavelengths of light, ranging from the microwaves, which are 0.1 to 0.01 millimeters in wavelength, to UV radiation that's in the scale of nanometers. And this ability to fit these ring resonators on a chip and scale up the manufacturing process is the technology that is currently driving the next generation of the internet.
Fast forward again, and I was pursuing postdoctoral research at Stanford with Professor Shanhui Fan. There, we focused on answering another question: how can we replicate exotic matter such as topological insulators using ring resonators? Throughout my PhD and postdoc research, there were so many stimulating questions that I felt inspired to build a team to explore these questions and push the boundaries of photonics at the quantum level.
Hi, I'm Sashank, and this is FLoQuET Lab. Since the group first started 2 years ago, we have grown into a burgeoning research lab that focuses on 3 broad fields: nonlinear, quantum, and topological photonics. Our major focus is on building chip-scale devices to really confine light at nanometer scales. So our lab does research on ring resonators to utilize them for exotic mechanisms like topological insulators, and even to generate exotic quantum states of light. So topological insulators were introduced in 1980s and were discovered when researchers sandwiched a 2D plane of electrons between semiconductors and applied a perpendicular magnetic field. As the magnetic field starts to increase, we see that bulk of the material is insulating, but around the edges, electrons start to show discrete conductance. So this is called a topological system because it is topologically protected. When you say a system is topological or topologically protected, this usually implies that the system's properties exhibit certain kind of robustness to deformations of some kinds in these systems. In our system, we can think of the topological protection as manifesting from any deformations to the structure. Say there's a dent in this two-dimensional material or this two-dimensional plane. One would expect that the electrons might reflect back and go in the other direction. But in a topological insulator, we see that it traverses the perimeter that's now deformed and continues to travel in this counterclockwise fashion. This is incredibly useful since it provides us with enhanced protection. This is extremely useful for manufacturing and allows us to extend the lifespan so that defects from manufacturing or use end up not affecting the device as much. One can also think of another use case for this where the efficiency of this process can be utilized where it only goes in one direction without any loss of electrons that are scattered back. And one can envision building electronic switches or new kinds of computing devices out of these kinds of topological materials. In ring resonators, we can envision utilizing photons instead of electrons to then harness a majority of the properties that we spoke about for topological insulators. Photonic topological insulators with ring resonators have a variety of applications. One such application is an improved laser. Now, lasers emit light at very narrow frequency ranges, unlike the light coming from a flashlight or even the sun. This is why you see the color of a laser is usually red or green light as opposed to the white light. Now, the more precise the frequency range and the more precise the phase that the laser emits, the better the laser is. And this is what enables a multitude of applications from chemistry and biology and astronomy all the way to self-driving cars and even the Face ID on your phone. Usually the optics inside these lasers are quite fragile. However, with photonic topological insulators, one could envision using our ring resonator structures to provide more robust lasers. So we know that photonic topological insulators provide a more efficient and robust mechanism to transport optical signals. But what if we wanted a cleaner signal from the source? This is where squeeze states of light, which are a different focus area of our group, comes into the picture. Now, we're all familiar with Heisenberg's uncertainty principle, which talks about the uncertainty or the precision in measuring any two quantities or two specific quantities of a quantum system. Typically, we think about the position and the momentum of a particle being uncertainty limited, but you can also think of a wave such as light and its frequency and amplitude being Heisenberg uncertainty limited. Now, if you think of light from a laser, you can think of it as a sine wave like this with a fuzz around it, which represents the inherent Heisenberg uncertainty. Now, if we wanted to measure the frequency more accurately, we could think of squeezing or reducing the fuzz here at the cost of a larger amount of noise or a larger amount of uncertainty in the amplitude. This allows for more precise frequency measurements, and this is really important for applications such as self-driving cars, where you use lasers to range and detect objects at a distance. In these cases, the object's distance is correlated to a frequency, and so a more precise measurement of a frequency gives more precise determination of the distance from your car. And it's pretty clear that these signals can be used for pretty much any sensing task to utilize the higher precision, and this has also influenced a lot of our group's research focus. These areas of research provide us a completely different way of generating, sending, and reading optical signals. It therefore has the potential to completely revolutionize the technology as we know it. Furthermore, the prospect of sending quantum states of light, such as squeezed light, into photonic topological insulators provides a completely new avenue of physics and applications to discover. Although our experiments mainly involve ring resonators, our broad research scope also includes theoretical and computational modeling and design.
Hola, my name is Rafael Romero Mendez, a junior in physics and math, and I work on modeling noise in photonic devices. Consider the camera this is being recorded. As clear as the audio quality might sound, there is still some unwanted information, something like noise. Noise is present from radio station to all TVs, and understanding how this noise affects data and coming up with ways to reduce it is essentially the development of any new technology. Particularly, my research focuses on understanding and developing a mathematical model that is able to describe the noise in photonic devices, such as ring resonators.
Namaskara, I am Samar Sriram, a rising senior. At the FLoQuET group, I try to understand if we can get photons to behave like phases of matter in higher dimensions. To do so, we use 1 or 2 ring resonators versus the commonly used 100 or more. Particularly, I study exotic phases of matter to see if we can emulate physics of dimensions greater than 3 in these resonators.
In this lab.
Yes, so take mode like separate state, that they do not get entangled.
That is the story of our lab and the researchers who are at the cutting edge of science and engineering. Now, what will your story be?